So welcome everyone, and thank you for joining us in this meetup. So I'm very honored to have with me today Mr. Faïcel Chamroukhi, who is a professor of statistics and data science in Caen. He is currently adjunct visiting professor at Trobe University, and has been assistant and associate professor of computer science and machine learning in Paris and Toulon. He is broadly interested in the mathematical and algorithmic foundation of data scientists and artificial intelligence, with a keen focus on modern statistics and machine learning. He has common traits of his research include statistical modeling and inference, latent variable models, and learning in high dimensional and large scale scenario. So today he will be presenting for us some statistical analysis tools of complex time series data. But before that, we will share with you a video which present Our Lady's Tunis, and which was made with R Markdown. So Hedia, can you start the video, please?
Welcome to this workshop session. Before starting the workshop, we'll introduce you to the Our Ladies Global and Our Ladies Tunis initiative. The R community suffers from an underrepresentation of minority genders in every role and area of participation, whether as leaders, package developers, conference speakers, conference participants, educators, or users. As a diversity initiative, the mission of Our Ladies is to achieve proportionate representation by encouraging, inspiring, and empowering people of genders currently underrepresented in the art community and to facilitate individual and collective progress worldwide. Gabriela de Caros founded Our Ladies on October 1st, 2012. Our Ladies Global was born and the grant was awarded in September 2016. Since then, Our Ladies has grown to 170 chapters in 44 countries and 39,000 members. Our Ladies Tunis is part of Our Ladies initiative and was created in May 2020 by women working as data scientists and biostatisticians and bioinformaticians. Our goal is to create an R community in Tunis and empower underrepresented genders in the R community. This is the core team of Our Ladies Tunis. Come and join our community on social media. This presentation was made with R Markdown. Thank you for watching this video and enjoy our workshop.
That was the presentation of Our Ladies Tunis. If you are curious about this presentation, Muna provides you the link of it in our YouTube channel. So let's move now to the presentation. So Professor Faïcel, the floor is yours and you can start now. Thank you very much.
Okay, thank you for the introduction. I'm just going to share my screen. Check if everything is okay. Okay, so everyone can see my screen now?
Yeah.
Okay. I'm just going to project the slides. Okay, so hi everybody, and thanks again for the nice introduction and for the video. It is always good to advertise for collective activities like those done by Our Ladies. And first, please feel free to interrupt me if you have questions, but it seems like we cannot really ask questions using audio, so maybe it is it's not too practical to interrupt at the end. Or maybe someone can read the questions and ask them. Or
Yes,
yeah.
that's what we will do. I will read all the. I will take care of the question. I will read all the question.
Yeah. Yes, please. I will be focused on my slides, and if there is a question on the chat, maybe someone from the organizers can read it for the
Yes.
people, the person who asks the question. And
yes, I'll be taking
so,
care of the question.
Okay, thanks very much. And I am happy to be here today and to give this online video talk. This is really my my online talk, and I hope it will be of interest to all of you. And the subject of the presentation today is to talk to you about some of models and the algorithms I did in my research, which are focused mainly on time series data. And yeah, I will tell you later what I mean by complex time series data. And I don't have any idea about the background of people who are attending this, this talk, but I suppose that at least they know about basic statistical models like regression and classification. That's all what you would need to understand most of what I'm going to present in my talk. Okay, and sorry, how to move this thing? Oh yeah. So as a statistician, I cannot start my presentation without saying a few words to advertise about statistics and data science in academia in particular, and also in industry. And today, these fields are taking a lot of interest in both academia and industry. And for example, in academia, I think some of you know about some worldwide initiative like artificial intelligence institutes or data science institutes, people who are at least maybe who know about the European system. They know that nowadays at least each university has its own data science initiative, and same thing in industry. And according to the very serious Harvard Business Review magazine, being a data science today is perhaps one of the top jobs in the private sector. And there is no, of course, there is no consensus on what is data science exactly, but we can see it as the study of how to extract knowledge from data and to generalize this knowledge on future data. And of course, yeah, sorry, I see that your videos on my slides. I'm trying to move them. Yeah. Oh no, maybe like that. So, okay. And yeah, how to extract knowledge from data, of course, requires many skills going from math, in particular in statistics, to computer science like machine learning and databases and optimization. And statistics and machine learning, they represent, I think, the core of any artificial intelligence or data science system to transform data to knowledge. Statistics, it represents, in some sense, the foundation of any model, of any machine learning algorithm. And the machine learning part, it represents the intelligence part in some sense. So statistics and machine learning allow to convert the data into knowledge. And in addition to that, you need, of course, skills like databases and parallel systems to store your data and for parallel systems to run your algorithms. Especially, in fact, today, you certainly heard about big data, and the question to how to deal with big data requires new strategies to store the data and to run queries on your data. And if you have a machine learning algorithm, this also requires some strategies to run your algorithm. And if you are interested by this topic, you can read the nice review of David Donoghue from Stanford. I think it is quite complete to understand this topic. So the conclusion is, if you are in this field and you are interested into how to extract nodes from data, you need to take care about statistical models and also about computer science part, that is machine learning. And okay. I'm trying to figure out how to finally remove this these videos. Okay. Okay, yeah, doesn't matter. I'm going to quit it here, maybe. Okay, so statistics play a central role in this field, in data science, because it is obvious to say that to quantify the randomness part in the data, you need a probabilistic model. And you would also need some theory to, for example, to evaluate your estimators if you are doing estimation, and also to see and to measure how accurate are your predictions. And for all these things, you need a theory. And in statistics, there is a very well established theory. And also, what we do when we try to extract nodes from data at the end, the objective is how to make decisions from this data. And when you make any decision from the raw data, you need to measure how accurate your decision is. And statistics offer you the possibility to measure the uncertainty in your decision. For example, if you are doing regression, you can construct confidence region around your fitted line, if you are doing linear regression, for example. And if you are doing classification, you can measure your uncertainty in your decision via, for example, the probability of your classes. Rather than, for example, saying it is a 0-1 classification, you can say, I'm in class 0 with, for example, 0.7 probability, and I am in the other class with 0.3 probability. And today, specifically, what I have called the statistical analysis tools for complex time series data, I will be focusing on complex data in the sense that they are heterogeneous. That is, the population, it is composed of many subpopulations, and so for our analysis, we would need to characterize the properties of each subpopulation. And in particular, the data, they present a temporal nature. They are by nature temporal. That's why we call them time series. And in the second part of my talk, I will show you how to analyze time series in high-dimensional setting. Another kind of complexity is that the data can be incomplete. Incomplete in the sense, for example, when you have a raw data set and you know that the data generating process, it involves, for example, a structure, the hidden thing is the structure. And the objective in this example is how to reconstruct the structure from your data, your raw data. So in some sense, the data are incomplete because we do not really know exactly what is the structure of the data, and we are going to restore or reconstruct it from the raw data set. So the objective is, from general point of view, is how to efficiently transform your data into knowledge. Efficiently, it can have a computational sense and also statistical sense. Statistical sense, you need to measure your precision in estimation and also in prediction. And it can also have a computational sense in the sense, if your estimator is okay, is, for example, consistent, when you need to implement it in a computer, you need to run it quickly. And your model and the results, it is always better when you can make interpretation of what you are doing, of both the models and the results. Because at the end, as a statistician, you are doing the job for another users. If, for example, you are doing the job with a doctor, the doctor, if he or she has not statistical skills, you are not going to provide him or her a mathematical model. You need to, it is always good to have interpretable things. I mean, no black box each time this is possible. And the objective, as I said before, specifically in what I'm going to present today, is how to transform the data into knowledge. What I call knowledge here specifically, it can be, for example, classification partition or a hidden structure. If, for example, the data came from a population which is composed of many subpopulations, if you identify exactly each data point came from which subpopulation exactly, in some sense, you reconstructed the structure of your data.
Sorry to interrupt you.
The structure, it can be a set of groups or hierarchy.
Sorry to interrupt because we have already a question from Asma who asked.
Okay, that's fine. That's good.
Yeah, she is asking if is it possible to apply data science and artificial intelligence to distribution logistics? If yes, how, please?
I think this question is general and at the interface of the topic of this talk, but I would answer, you perhaps can apply data science and artificial intelligence each time you have data. If you have raw data, there is always a way to have an informative summary of your data. And about logistics, I'm not an expert of the field, but in statistics, what we are doing is what we call a generic model. When you build a model, the difference in statistical analysis compared, for example, to other what we call system analytics, we build generic models. You don't construct a model for a specific task. Your objective is to construct a model so that it can be generalized on other tasks. So my answer is, I think yes, provided you have data from your logistic task. And I think yes, nowadays we have always data, I think. Is that okay? Okay, so, and more precisely, now I'm going to be maybe a bit mathematical. I'm going to introduce some mathematical notations. The models I'm going to present, they are some specific models which are included in the family of what we call latent variable models. So what is a latent variable model in general? A latent variable model is when we assume that, do you see my mouse here? Okay, so if, for example, we denote by x the data we observe, we assume that the observed x is a marginal observation of a more general process, which includes another kind of data denoted z, but z is hidden for many reasons. Z, it can be unknown, it can be hidden for privacy reasons, it can be hidden because we know it, but we do not wish to distribute it, etc. So if you are in this setting, you are modeling an observed data, but you know that your modeling, it depends on another kind of data, which is not directly observed. This is the general framework or latent variable model. And it can have another representation. And that's why what we call the latent variable model a generative model, because this notation here is equivalent to assuming that you observe some data x here, and you know that this data x depends on another unknown or unobserved or hidden data z, and given z, your observed x is distributed according to a parametric distribution f. Its parameters are theta. And z, the unknown variable, it has its own distribution, denoted q, for example. It can be parameterized by theta. It can be non-parametric too. So this framework is of very big interest to me because it accommodates very well the estimation questions as well as prediction and selection questions. I mean, we have mathematical background to do all these tasks with latent variable models. And the other important point to me, this latent variable model is by nature generative. It can explain to you how your data are generated. If, for example, you have a customer and you need to provide him a model, statistical model, your customer, if he or she doesn't have enough data, he can use your model to generate data. And at least this generative formulation can help you understanding how the data are generated.
Before moving,
so what I'm going to
sorry. Before moving, we have also a question about latent variable. So Skander is asking if you can give us a concrete example from the real data world of a latent variable.
Yeah, a concrete example is the mixture of Gaussians. If you know about mixture of Gaussians, maybe it's maybe you certainly know K-means for clustering. The probabilistic extension or the probabilistic version of K-means is the expectation maximization algorithm when you use it with the mixture of Gaussian distributions. This is a typical example for latent variable models. In the mixture distribution, you assume that you have a set of finite number of distributions, but you do not know exactly which data comes from which Gaussian distribution. So a first complete example is the mixture distribution. And we use it in clustering. It is the typical model, it is a model of choice in clustering. Another very popular model, which is a latent variable model, is the hidden Markov model. You can use it in speech recognition, for example. And today, another very popular model in the neural network in the deep learning community is the variational autoencoders, the autoencoders or the variational autoencoders. All these models are latent variable models. I don't know if this asks your questions. No?
He said no, unfortunately.
So the question was about a concrete example about latent variable model?
Yeah, but he is thinking it's theoretical. I don't know about
Yeah,
real
let
data
me give you this
world.
example. Yeah, do you see this data set? See this data set? I'm going to cluster it. Clustering is the fact of telling each data sample comes from which cluster. I can apply the so popular k-means. Maybe some people know k-means?
Yeah, for sure.
Yeah. So when I apply k-means, I summarize my data set, for example, here into two clusters. Each cluster is summarized by each mean location. This is k-means, and that's all. A latent variable model with k-means, I cannot measure the uncertainty in my classification. I have a hard classification. At the end of your k-means, you know that this blue guy, he belongs to this group, and that's all. You cannot measure the uncertainty in your classification for this guy or this one. However, when you use a latent variable model, for example, a Gaussian mixture model, so this is k-means, and I'm going to skip it. So now the question is, rather than using a deterministic allocation like in k-means, we are going to use a probabilistic model for clustering. And like that, we can measure our uncertainty in classification. And the typical model is what we call a GMM, the Gaussian mixture model. Okay? And the Gaussian mixture model, this is the result of Gaussian mixture model classification. And the Gaussian mixture model, it is written like that. Here is the density of Gaussian mixture model. And this is a latent variable model because you assume that you have, for example, here 3 Gaussians, but you do not exactly know, you don't know exactly which data it is generated by which Gaussian. So here, it is the notation of this Gaussian mixture model as a latent variable model. You assume that your classes, they are distributed according to a multinomial with some weights, and given a class, if you are here, for example, you know that your observations are generated according to a Gaussian. So this is all what I can say about an example of latent variable. Yeah, that's it. Okay. Yeah, and and now I can go perhaps more in detail about the main topic of this talk. The first part will be on time series segmentation, and the second one on time series clustering. And for time series segmentation, I will present you some models we introduced in the literature, and all the things I'm going to show are implemented in Samurai, and if I have time, I hope I have enough time, we will try them together. And the thing of time series segmentation, the context is this one. Suppose you observe data like that, like this one, or this one, or this one, etc. And here, as you can see, the observation, they are by nature temporal data. And the specificity of what I am going to present is that it's not all of the time series, of course. We are focused here on time series who are heterogeneous. Heterogeneous in the sense, look at this time series. You clearly see that there is, for example, a jump from here to here, and the same thing here. And here, you clearly see that there is the variance here in this part is clearly different from this part, and same thing from this. And look at also at this example. You see that there is a kind of regime here, and then another one, and etc. So heterogeneity here is really clear. And you can, for example, look at it here in this multivariate example. Of course, the data, they can be univariate or multivariate. And so, if you look to this part, the jump here is very clear from here to here, but it can be, we can have a jump here, I mean a regime, what we call a regime change here, but the change or the transition, it can be smooth. So the objective here is how to deal with time series with unknown regime changes over time. And the regime changes, they can be abrupt or smooth. I mean, they can be quick or they can go smoothly. And this is a problem of time series segmentation. And to do segmentation, we need a model, and as every model, we can approximate the time series if you would like to do that. And according to our context in latent variable models, we are going to assume that the data we observe, it is generated by an underlying process. And precisely this underlying process, it represents in some sense the segments. For example, here we are going to say there is a first segment here, second one here, etc., and the last one here. And the objective of the model is to obtain this segmentation. And in the state of the art, for notation, we are going to assume that the data we observe at time t is denoted y, and y, for instance, is a scalar, is univariate time series. And piecewise regression is perhaps, the baseline or in this framework. I'm going to go a bit quickly on this slide because it's not the important of the contributions in these slides. Piecewise regression is too simple. You assume that you have a sequence of lines or of polynomials which are corrupted by noise, typically Gaussian noise. For example, in this time series, you assume that you have first polynomial, second one, third one, etc. This is a polynomial regression, this is the second one, and this is the last one. And we assume that we have a capital K segments. Each segment is described by this set of parameters beta and defined on the set of time location gamma k till gamma k plus 1, and the noise is assumed to be Gaussian. So all the job is how to place your polynomials here at the good locations gamma k and gamma k plus 1. And if I can say, from a mathematical point of view, the question is to perform the segmentation is to estimate the parameters of the model, that is the regression parameters beta, the variances sigma, and the transition time points gamma. And we can do that by minimizing this kind of squared error. We can minimize that globally by dynamic programming. Globally, I mean in an optimal way. However, dynamic programming can be expensive, especially for large time series. And another disadvantage of this approach is the classification is hard. The segmentation is a hard segmentation. It is a 0-1. You cannot have a measure of your uncertainty in the segmentation. And here, how the thing works, and if you look to this green curve, here is the original data. And
sorry, we have also a question. Skander is wondering if the gammas giving randomly or are choosing.
No, the gamma are determined by the algorithm. The gamma, they are determined by the algorithm. The gamma, they define, the gamma, they are exactly these things. The dashed line, the dashed lines, they are the gamma. Actually, all the question is how to determine the gamma, and accordingly, how to determine the beta and the sigma. I don't know how to go back. So all the question is how to estimate these things, the gamma, the temporal location, and given the temporal location, so given the segmentation, how to fit the correct polynomials here, okay? Yeah, so you take your curve here, here is a toy example, and here is a real example. What the algorithm do is, it takes this time series, and it simultaneously fits a series of polynomials here, and at the good locations. And the good locations here in dashed lines, they represent the gamma. And the polynomials here, they represent the beta and the sigma. The beta, the regression coefficients, and the sigma, it is the noise variance. Sigma, it measures the noise variance here. And roughly, you are like adjusting many polynomial regression at different locations. And these locations, they are calculated by dynamic problem.
We are having another question from Ayman.
Yeah.
He is asking how to choose the right K.
Yes.
The right K. Well.
Big and very good question. Look, yeah, how to choose K? Choosing K is like determining how many clusters or how many segments in the data. And when given a fixed K, if K is fixed, we optimize this criterion J, okay? And this criterion actually is the negative log likelihood. And so we have the log likelihood. To choose K, we can use what we call the Bayesian information, the criterion, which is a kind of penalized log likelihood. Precisely to choose K, we take this quantity and we penalize it by the dimension of the model. Dimension of the model, it represents the number of free parameters. So it is directly related to K, and also by the number of observations. I will present the BIC, the Bayesian information criterion, later. Okay?
Yeah, I think it's okay.
So my answer is to choose K, we can use a model selection criterion like BIC, Bayesian information criterion, because this is a probabilistic model and we have a log likelihood. Yeah.
We have another question from Skander, who is asking which dynamic programming algorithm is used to calculate the gammas.
Yeah, we used some kind of Fisher, what we call the Fisher algorithm. It is quadratic in the number of observation. But perhaps since we did that, I think in 2010 or 2009, maybe since there is more optimized versions of dynamic programming. We used the Bellman and Stone principle, that is an optimal partition in K segments is an optimal partition in K minus 1 segments plus an optimal fit in 1 segment. Okay? I mean, we use the standard Bellman and Stone principle of dynamic programming. Okay. And a remark on this, so I said this thing can be computationally expensive, piecewise regression and dynamic programming, and it's not probabilistic. Look at this result. I have a segmentation and a fit, and that's all. I can't measure uncertainty here, okay? What we can do is we can generalize, or we can extend our modeling of the segments by using probabilistic process, statistical process. For example, in our piecewise regression, we used it before, we assumed here the notation k. That means we have a fixed number of segments denoted by k in a deterministic way. Here, what we can use is we can assume that each observation I has a label or a state Zi, which is unknown, and the sequence of states Z1 till Zn is a Markov chain. And when we do that, it is a hidden Markov model in a regression context. And this model works quite well, and we can fit it in a maximum likelihood setting by Baum-Welch algorithm, which also I call the expectation maximization algorithm. So I will not give much details here, but this model can be fit in an efficient way, and yeah, and the algorithm is quite effective. The thing is that if we have very structured data like these ones, when you use the Markov chain, there is a hypothesis which says that your sojourn time in each regime is geometrically distributed. That means it can have it tends to switch into the other state quite frequently, and so it cannot be suitable really to very structured time series. And other thing, when the transition from one state to another is smooth, you cannot explicitly measure that, at least compared to what I am going to show you. So here is our perhaps preferred model, and the difference compared to piecewise regression is that we use a statistical process for the hidden variable, and the difference compared to the hidden Markov model regression is that our modeling of this statistical process is not a Markov chain. We use it as a multinomial distribution, and the thing here, the probabilities of this state, of this segment, they are calculated according to the multinomial logistic. Some of you maybe can call it the softmax. It is a softmax. And to understand how this thing is suitable, you can see, for example, if we take different values of lambda and different values of gamma. The gamma here, it doesn't have anything to do with the one of piecewise regression. It is another notation. And here, if we, for example, for a fixed gamma, if you take gamma fixed and you vary lambda, you can have, look, here you can have abrupt change, and you can have also smooth change. And if you fix lambda, that means you take this degree of smoothness, this one, and you vary gamma, you can look here, gamma is directly related to the segmentation, to the transition point. For example, for gamma 1 equals -3, and -3, that means the transition is at 0.3. Same thing for -2 and -1.5. Okay, this is to say, in our modeling of the probabilities of transition of our segments Z, it allows to take into account smooth transitions and also abrupt transition. And also it allows to segment as the Markov model or piecewise regression. So now the model is defined. I don't know if you have a question on the model. If not, given this model, the distribution of the data, we need the distribution to fit the model. To fit the model by an estimation approach, we need to know what is the density of our observed data. So the density of the observation Y at time t here, it is this kind of mixture distribution. Okay, and what is interesting, sorry, in this kind of mixture distribution is that the proportions here, they depend on time. Okay, and also look at this Gaussian. The mean, it's not constant. The mean is a regression. The mean is a polynomial. And x, this co-variable, it includes time. And now, all the question is how to estimate theta from the data. and we estimate it by maximum likelihood. Okay, we maximize this likelihood, and we can do it. We have the algorithm to do it, but the algorithm in one line is this one. The algorithm is what we call the expectation maximization algorithm. How do we have how long I must? Now it is 7:28. It is okay. I mean, if there is a rush, please tell me. Okay. So the algorithm is, we estimate the parameters in an iterative way, and at iteration Q, what we do is that we first calculate the expectation of what we call the completed data log likelihood, given the observed data here and the current parameter, and then we maximize it. Okay, and this algorithm is actually very smart, and it goes back to Dempster, Blair, and Rubin, who invented this thing in 1997, and we adapted it to our setting. And it is smart because you can restore, in some sense, the hidden data by maximum likelihood. They find a way to perform maximum likelihood when there is missing data. And in practice, for our model, this EM, it is called EM because there is two steps, the expectation step and the maximization step. Without going into details of these mathematical things, maybe some of you or most of you are not familiar with that, this slide is to say, at the expectation step, we only need to calculate what is the probability of being at segment K given observation R. Okay? Given the current observation, what is the probability of being at segment K? And this probability, what we call tau, in other contexts, some people in machine learning call it the responsibility. These responsibilities are calculated directly and explicitly. Okay? And then at the M step, remember that the M step is that we need to maximize this quantity, the expectation of the completed data log likelihood. And the M step, if you look carefully to these quantities, they resemble a lot to polynomial regression. If you remove tau here, remove this thing, you recognize the ordinary least square estimate. It is like you are doing regression. So why you have tau? Because you are trying to fit a polynomial regression to a data, but this data, they don't belong to the same group. And so you are weighting your data here, you are weighting them by the degree of probability to belong to class K. Okay? If you estimate the parameter for the polynomial K, you do a polynomial regression and you weight your observation by the probability to belong to segment K. And the same thing for the variance. Okay? So now we updated the parameters of the polynomials. And remember, in our way of modeling the segmentation, we used the softmax, the logistic regression. And so to update the parameter W of logistic regression, PK, here is the logistic probability. We need to update W, and maybe you know logistic regression. Logistic regression, we cannot solve it in a closed form. We need an iterative algorithm. Okay, so here is the same thing. We use IRLS algorithm, the iteratively weighted least squares, which is a kind of Newton-Raphson algorithm. Okay, so this is the algorithm. And what is interesting is this algorithm is not quadratic in N, while the piecewise regression is. And yeah, now if you have a fit of your model, you can do as in standard regression, you can approximate your curve by calculating the expectation. And here you have the formula for this model. And to perform classification, to calculate the segmentation, to know observation why it belongs to which segment, you need to maximize your logistic probabilities. Okay? And now, I come to how to select the best value of K and P. I forget if Skander or another, I think another guy asked me this question a few minutes ago, how to determine K. So how to determine K, we maximize the BAC criteria. So BAC is defined as, this is the log likelihood, it is regularized by this thing. And what is important in this thing is that we have here nu theta, and the nu theta is the dimension of the model. Okay? And so, as an example, what's this? Something is going on.
Mr. Faisal, we have another question from Iskander. He is asking, are you looking to segment the time series or to model it?
Yeah.
Yeah, he is asking.
Sorry?
Yeah, he is asking if you are looking to segment the time series or to model it. I think the answer is we are looking to segment the time series, right?
Yeah, I don't know the background of who's asking the question, but this question is really smart. And yeah, here I am segmenting the time series via a model, but my model and the estimator is consistent. So the estimator is consistent. I mean, asymptotically consistent because it is the maximum likelihood. I'm focusing on estimation and then the segmentation. When I use another kind of algorithm, which I don't present here in these slides, I don't use the expectation maximization. I use the expectation classification maximization. In this other algorithm, I can say I am focusing on the segmentation. I mean, I don't care too much about the estimation, but I look more for the segmentation. Here, I look for modeling, so estimation and segmentation. And I estimate before, and then I segment the time series. I hope this answers your questions. It is always difficult to don't know the background of who is asking the question. Because in statistics, especially in mixed models, we have some models in which we are focusing more we are consistent in estimation, and other ones we are consistent in classification or in selection. And so now I am back to my example. If I may.
I have a remark. For the question, we will leave it to the end of the presentation because we have only an hour. And I think if we will interrupt you every time with a question, we won't finish it. So please, everyone, would you ask all our questions in the chat? So everyone, please leave your question in the chat room, and we will ask it later because we have to finish the presentation first.
Okay. Actually, we don't have to finish. I mean, people can be satisfied by less than all the presentation. But it is always good to ask the questions. And I agree with you, Haifa, maybe it is better now to keep them for the end. So now I am back to my example. If I take a time series like that, I take two abrupt changes here at the end, and we assume that there is two other ones here. And if you look to the result, we fit these polynomials here. You see that the jump from the blue one to the green one, it is almost 1 or 0 probability. Here are the probabilities of being in one segment. And if you look to this part, of course, the transition from the blue line, sorry, it is tricky, huh? Sorry. Oh. Yeah. If you look to the transition here from the green line to the red line, it's not really obvious. So this uncertainty, you see it here. So look to these probabilities. They are far from 1 and 0. Okay. And yeah. And this is another example. Yeah, the curves I presented at the beginning of my presentation. So here, if I take this first curve, look, for example, here, you can detect the change in variance here. Okay, and there is a quite smooth change here from this regime to this one. And you can find even some locations here. Actually, these signals or these time series, they represent the power measured on the motor of what they call the switch of a high-speed train, French high-speed train. I did this thing in my PhD. And the objective at the end is how to prevent the faults in this device. Okay? I hope you like the examples, and more importantly, I will try at least to show you how it works. Oh yeah, this is what I call a generic model. We can also apply it on other kind of data, and here these data are related to fuel cell lifetime estimation. And the transition here, there is a kind of abrupt one, not too much abrupt, but enough abrupt. And there is another one here, which is smooth, and we detect and we approximate. And now, as an extension, the examples I showed to you before, they represent univariate time series. And we can do almost the same thing when we have multivariate time series, like in these examples. For example, imagine you measure the acceleration data of a moving person given from some sensors on the body. And for example, we have the 3D acceleration. Over time, here we have about 25 seconds of acceleration data. The idea is how to segment this thing, and now we are in multivariate setting. So we can extend this stuff in a very easy way. I mean, including polynomial regression, piecewise regression, including hidden Markov model regression, and the model, the regression with hidden logistic process I just showed to you. And it works. Yeah. And now, okay, I at least have a few minutes to show you this thing. Everything is written in R, at least, also written in MATLAB, and some of them are written in Python and are available in open source. And if you can click on, for example, on GitHub, and to show you how to run this thing. I don't know if some of you have already installed Samurai, at least Samurai. Maybe yeah. No. Okay. Yeah. It doesn't matter. It's not too important. What I want to show you is you can install it from the CRAN. It is available, and how to use it. I think it is too simple. For example, here Samurai, it integrates the model I showed you, piecewise regression, hidden Markov model regression, and the regression with hidden logistic process. This part concerns the univariate models, and this part concerns the multivariate models. There is also the multivariate piecewise regression, which is separated from Samurai. And the way how to use it is too simple. You take your data x and y, x is the input and y is the output. So the pair x and y is the time series, and you say how many segments you need and what is the degree of your polynomial. Q is always fixed to 1. Don't care about this parameter. And these are some, how many runs of the algorithm, don't care too much about this. And then you run it, you obtain a kind of summary of your data, log likelihood, the values of the model selection, and how many data per segment, and the regression coefficients for each segment, and the variances, etc., and some plots. The plots similar to those I have already shown you. Okay, and another thing at the end, maybe this is, I think, the model selection. The model selection part, it shows to you, for example, for RHLP, how to use it in an automatic way. Don't care about how many segments and what is the polynomial degree of your regression. You just give it the data, X and Y, the time series. You just give it a range of your number of segments. For example, you say it is between 1 and 10, and the range of your polynomial degree, and that's all. Okay. And that's all. And you have also some real data they are available. Okay? And yeah, this is on Samurai. Yeah, so maybe I must stop here for a question, because the second part, I realized I was too optimistic maybe about finalizing the two parts, but yeah, a few words about this part.
I want to add something. Sorry for interrupting you. In fact, for us, you are allowed to stay about 2 hours using this Zoom account. Sorry. So no worries about the time, because I feel like you are
We still have 45 minutes.
Okay, so I will spend only 15 minutes more on showing you this thing, and then I will let you ask me questions. Yeah. So for this part, the difference is compared to what I presented before. Is now I am interested in the situation like that, in which we observe many time series. Okay, and the question is how to classify these time series in an automatic way. Okay, so this topic is often called functional data analysis, and we can find all the statistical problems like in standard statistics. I mean, regression, classification, clustering, in graphical models for functional data. And we have wrote with my colleague in a review, and you can look at it if you are interested in this setting. So the objective here, if I have a set of data like that, like this one, how to classify it? And how to classify it, I'm going to use mixture distributions. I assume that each curve, each time series came from K components, capital K clusters. And since it is a mixture distribution, again, we can use the expectation maximization algorithm to classify this data. And the first thing, yeah, I'm going to move quickly on this part. Yeah. The interest and how everything works. Yeah, if we look to this example is a set of time series like data, and it corresponds to some measured echo of waveforms from top exposed satellite data. It is a kind of satellite data, and at different echoes you measure, at different frequencies you measure some echo. And the objective is how to provide an explanatory analysis to this kind of data. It is a kind of descriptive analysis. And if you look to this data set, you cannot really understand a lot of things. However, by using an adapted declustering technique, which takes into account that each observation is itself a time series, you can find an informative summary like this one. And this is an example of results we obtained in one of our previous work. And if you look at this summary, here, for example, we used 20 clusters, I think. Yeah, 20 clusters. And if you look to these clusters, you can find those who correspond to, for example, like a narrow bond, and like maybe a bit large one, something like a constant behavior, there is a jump, etc. At least it is clear that between this one, the raw data, and this one, you would prefer this one. And so clustering of this kind of data is really of interest. And of course, you can do this when you have a regime switching, etc. But even if your curves are smooth, like this data set, you can obtain a quite smooth approximation here. Look here, the lines, they are quite well joined. And you can even interpolate and optimize this. And yeah, so this is another example. The question here, these examples, these time series, they came from a railway diagnosis application. The question is, if I have a data set like that, can I do a first analysis to show if there is some common behavior? So like that, I will not labelize each time series by hand. And the answer is yes, it's possible to run this kind of algorithm on this data set and to find these two clusters, for example. And these two clusters, you can look, there is at the end a kind of a peak, and this peak can be of interest to the experts. And the other thing is that it is a simultaneous clustering and segmentation. From this data set, we have a clustering here, and within each cluster, we segment. And the segmentation, it corresponds to the real functioning process of the motor of this kind of high-speed train. And yeah, this model, it works quite well, and the algorithm is quite efficient. However, it's not fully probabilistic, in the sense that for the segmentation, we use a dynamic programming. And to make all probabilistic, we have proposed this model. It is a mixture model. We have a complex sum of distributions with weights alpha k. Each distribution is a regression model with hidden logistic process. So simply, we are going to cluster the curves yi into k clusters, and within each cluster k, we are going to segment it in rk, I subscript k regimes. And since it is a probabilistic model, and precisely it is a mixture model, we can estimate it by the expectation maximization algorithm. Okay? And yeah, now the weights here, the logistic weights, they represent the probability of, if I am in cluster K, in a homogeneous group K, it is the probability that the observation J comes from regime R in cluster K. It is maybe a bit complicated to understand, but it is too simple. Provided I am within cluster K, I do segmentation through this random variable H. This is equivalent to the former Z in RHLP model. Okay, so here we have two kinds of memberships. For curve I, or for time series I have the label Zi, and within cluster K, I have the label H for observation J. And the algorithm is, yeah, here is the algorithm. It is an expectation maximization algorithm. So there is an E step and an M step. And in this step, the difference compared to before is we need to calculate the probability that a curve belongs to cluster K, and the other probability is, given I am within cluster K, what is the probability that the observation at time t comes from regime R? So here there is clustering and segmentation, and both are done simultaneously. And at the end step, I update the weights alpha k of the mixture distribution in a standard way. This is standard way common to any problem. I mean, including our time series problem. And then I update the polynomial coefficients and the variances. It is an analytic weighted least squares problem. And for sigma, it's like we are doing least squares, but in a weighted way. And to determine the parameters of the logistic function algorithm. And yeah, this is some kind of simulation. If I take a set of curves like that, I can cluster it into two groups like this. I can obtain smooth curves, and I can obtain also some kind of, a mean curve with abrupt changes. And these are just measure of accuracy to say that everything works. Yeah, this is the example as before for piecewise regression mixture. If I take a data set and I run the mixture of regression models with hidden logistic process, I can obtain this kind of clustering. Okay. And yeah, I think I must stop here because this part is just to say this model can be used in clustering, and if I know the labels, if I know which time series belongs to which class, the problem becomes really obvious, and we can do classification. I mean classification in the supervised way. Okay, and these things are implemented in Flamingo, the package. Yeah, you can, by the way, remark that I like using some funny names. Yeah. And so in Flamingo, Flamingo is available on Cloud, and it is also in GitHub, and it implements all these mixture models. I mean, the mixture of hidden Markov models, the mixture of hidden Markov model in a regression context, and the mixture of piecewise regression, and the mixture of my preferred model in some sense, the regression model with hidden logistic process. And recently, I also provided the unsupervised learning of regression mixtures. And in here, we learn regression mixtures by also estimating in an automatic way the number of mixture components. And you can check it on GitHub, and how to use it. It is too simple. You download the algorithm, and then, yeah, you provide your set of curves. Here, Y is a matrix, and you cluster it in 3 clusters. And within each cluster, you look for example, 3 regimes. And you use linear or quadratic or polynomial regression. And this guy is always fixed to 1. We just put it here because it was the first version of the package, but we are going to update it. And then you obtain things like that. Yeah. Here, for example, yeah. Here, this is the whole data set. And when you perform clustering, you obtain 3 clusters here. And within each cluster, an approximation and also segmentation. Okay. Yeah, you have the segmentation here for each cluster. This is cluster 1. There you have the approximation, the segmentation. As you can see, the probabilistic segmentation, it accounts for the smoothness of transition here. Okay. And the same thing here. Look, here the transition is abrupt here, and you can see that you can see this also on the probability. It is almost 0.1. And when it's not too much, too clear too much, you can also see this uncertainty and the probability here. Yeah, same thing here. The jumps, they are very clear in the segmentation. It follows accordingly. And the log likelihood, it is the optimized criterion to ensure that it is always increasing. Exactly. Yeah, there is also the mixture of hidden Markov model and the mixture of hidden Markov model regression. And I hope you will only find them on MATLAB or also on Python. Yeah, okay, so that's all. And some references. And yeah, thanks again for your attention. And I hope this talk was not too heavy to you. And I hope it's not too theoretical. Yeah,
Thank
but at
you.
least as a first online video talk. Yeah, thanks. And I'm ready for the questions.
Thank you. We have a few questions from Ayman, who is asking if we change the model selection criteria, can we have different results for K and P? And why are we choosing BIC as default model selection criteria?
Yeah, I mentioned. Yeah, actually, the model, the algorithms include 3 model selection criteria. You can use AIC, a KK information criterion. You can use also BIC, the criterion of Schwartz. You can also use ICL, which is another criterion based on the calculation of the integrated classification likelihood rather than the likelihood. It is called the ICL. And so I don't choose the way how to select. I provide the 3 criterion, and it is, I let you choosing which one you prefer. And about the question, which one, I mean, the question, if I modify the criterion, can I or would I obtain different results? I think yes. And the most important question is what is the difference in the behavior of BIC compared to AIC or ICL? I think BIC has some consistency results, at least in mixture of Gaussians. I mean, if you have enough data, you are expected to obtain, when you are using BIC, to obtain or to converge towards the exact number of clusters. So here, the exact number of segments. And I honestly don't know about such consistency results for AIC. For ICL, in the multivariate setting, when your clusters are quite well separated, I think using ICL can do it, and BIC can be advised when your classes maybe are, are mixed enough in some sense. Yeah, I don't know if this answers your questions. So if you modify, would you obtain different results? I think yes, it depends on the situation, because they are not exactly the same. The other question is which one is better? Again, it depends on the situation, but from the theoretical point of view, I personally would, in some situations, prefer BIC, because I read about some papers in of consistency, at least in the Gaussian mixture of Gaussian scales. And if the clusters are quite mixed, it can do it also well. And for ICL, where they are quite well separated, you can use also ICL.
There is another question from Skander. He was asking, do you think that this kind of model is suited for financial time series?
Oh, honestly, I'm not sure, but it depends on which kind of time series, of financial time series. I know, for example, some work of Jean Jean-Pierre, no? Bardet, Jean-Marie Bardet, I forget his name, Bardet from Paris 1 University. He is interested in detecting the regime changes. And from this point of view, we can do also segmentation. But if the objective is to detect, the volatility, or I don't know which kind of behavior, I think there is some more dedicated financial time series models compared to this one. This one, there is a strong hypothesis behind the model. The data they represent, a kind of strong structure. Very well, the data, they are very well structured.
Great.
We are detecting, in some sense, changes in the mean, changes in the variance, and yeah, mainly, and changes in the transitions. For financial time series, I think we can, some people, they can be looking for other things.
Great.
Great.
And so you have here Mr. Fuad saying, thank you, Dr. Faisal, for this excellent presentation. I hope you can see you among us very soon at the Department of Statistics of King. This is a nice invitation.
I would love to, yeah. When this pandemic will disappear very soon, I hope. Yeah. Well, once the health situation allows that, I would be very glad to get in touch. And yeah, thanks for it. Very much appreciate.
So, if you have another questions, please don't hesitate. I think you are done with the questions. Is it okay? I would like to thank you, Mr. Faisal, for this great presentation.
Thank you to you, and I very much thank you and thank all people who attended this online course.
Yes,
very much.
I hope that it has been useful for all of you.
Yeah.
Okay, I think there is no more questions. So we'll be sending you the recording video later and providing you again with the link for the presentation. And thanks again for all of you.
Thank you, everyone.
Thanks to all of you too.
I think there is a question.
Yeah, we have a question from Tawfiq.
My question from Tawfiq is, yes, sorry.
I will go ahead for
if you.
So Tawfiq is asking if we can do feature selection.
Yeah, I did feature selection in an extension of this model, but not for this one. In the multivariate case, on this one, we worked with all the dimensions, but in work, which I don't present here, yeah, we do feature selection. I have some, I think a couple of papers with my former PhD student, twin. Yeah, I think you can look at them if you want. But this model is a kind of a mixture of expert model. And what I did with twin is a mixture of experts in a high dimensional setting. I think the title of the paper is something like maximum likelihood estimation, no, regularized maximum likelihood estimation and feature selection in mixture of experts model. So the answer is yes, but it's not presented here, and it's not included in Samurai nor in Flamingo, but the codes are provided in open source on GitHub.
Okay, Luciana is also asking if you have published a paper related to feature selection.
Yeah, I can look at that few. Sorry. Oops. Just. Yeah, I can. So you have this one. No, maybe. Yeah, feature selection. Yeah, there is 3 things. Where is the third one? Let's see. Yeah, there is at least. Sorry. Maybe the only view. Do I still have the screen share?
Yeah.
Yeah.
Yeah, we are.
I'm trying to send you the. Can you send me a message like that? I can answer. Yeah, I don't see the
maybe
icon
because you have to exit the presentation mode.
Yeah. Oh, okay. So look, the answer to Luciana is yes. We have published, I think, a couple of papers on feature selection, and you have them on the screen. You can just go to my web page, and you have the first one is regular system and feature selection, and perhaps this one is more adapted to because it is most close to this talk.
Yes,
And
we
there is a
will.
third one, but it is in the list. So
Okay.
the answer is yes. We did some things in feature selection on this kind of models, and we also have code online. The code I think is in this one.
Yes, Luciana,
Yeah,
we will share. We will share the webpage of Dr. Faïcel with you when we will send you the training materials of this section.
She's asking about the web.
You cannot see my screen?
Yes, we will share the link with all the the link of the web page of Dr. Faïcel with all the participants later with the training materials of this session. Okay. So no worries. We will send you all the recording of this session. Also, we will share with you the webpage of Mr. Faïcel and also the GitHub of Samorize and Flamingo. So you can try it by yourself.
That's fine. Thanks.
Dear participants, we want also to let you know about our next meetup that will be organized about TADI models, machine learning, on the 25th of November. So it would be next, not next
Not
weekend,
next Friday.
next week. I think the after, yes.
Yeah.
So, yes, so I will come.
We still have questions. Ahmed is asking. So he said, I see that you're interested a lot in time series of railways. Are these data collected by prisms and total station? He is interested in topography domain. So I think he's asking about the source of your data.
Actually, what I presented, there is railway data, there is energy data, and there is human activity recognition data. So it was not too specific to railway. And so, what is the question? The question is, can this be applied to geographical data? Or I don't hear very well the question.
He is asking if the data is collected by prisms and total station.
By presence and by presence and
By presence and total station.
Yeah, I think in what I presented, at least what I know, this. What is the slides? Look, if you look to this data, yeah, here, both of these things, both of these things, these two data sets, they represent ride-wide data, but as you can see, they differ a bit. They are not the same. I think this one, it comes from a different system compared to this one, but I don't know it. Actually, I know a bit about, I think this one should be TGV Nord, I think the one from Paris to Lille, and this one I don't remember exactly. I know that at least they concern two different systems of high-speed railway train, but at different stations. I forget about that, honestly.
So I think
But if you are working in the right way, I would be glad to have a chat with you.
So we will also share with you, if you don't mind, Dr. Faisal, we will share also our your web page and your Twitter and your LinkedIn page. Maybe they want to ask you other questions.
I mean, feel free to.
Okay. So I think that's all. So thank you everyone
Yes,
for.
thank you.
Thanks again to everyone, to all of the organizers.
So thank you everyone for joining us in this meetup.
Thank you all.
And have a nice evening and a nice weekend, and see you soon in our next meetup, the 25th of November. So you will have a meetup about machine learning and tidy models. We will be happy if you join us. Thank you very much and see you soon. Thank you.
Thank you for all
Goodbye.
participants. Thank you so much. Bye.
Bye.